This installment is going to cover logistic regression, and logistic regression is the analytical technique, the multivariate analytical technique we use when we have a dependent variable with a dichotomous outcome. Boy, was that a lot of jargon. Basically, when we want to explain something that has a yes or no outcome or a either or type of outcome, we use a prediction model that is specifically designed for that. And basically, what we're going to do is talk in this particular installment about how we can predict the likelihood that an event will happen based on changes in the various values of the independent variables. And the way to think about this, just to give you an example, let's say that we're trying to figure out whether or not you're going to vote in the next election, or for that matter, whether anybody's going to vote in the next election, and we've got a handful of variables in a model. We might say, in the general population, the probability that, let's say, a man would vote is 50%. And the probability that a woman would vote is 55%, and people who have a college education, it's 65%, and so on. And because we've got all of those variations that are going to impact one way or the other the probability that you're going to vote, we might want to answer the question of, if we were to hold the influence of all those other factors constant, then what would an increase, let's say, of each additional year of education do to impact your probability, or rather your likelihood of voting? So what we want to know is, for every increment increase of an independent variable, how does that affect the likelihood of an outcome happening, holding all other variables at their mean average of influence, which means for people who are highly educated, we're going to lower their education a little bit. For people who are, actually I used education, that's the independent variable we're going to look at. If we were looking at, for example, the influence on income, and income has a correlation with voting behavior, we might say, well, let's take the very wealthy people in our survey, and let's assume that any model involving them was going to overestimate their probability because of their wealth of voting. And let's take the folks who are of limited means, and let's artificially, statistically boost them up to the average so that we take out the effect caused by their income. If we do that to all of our cases, holding all the other variables at their constant, let's figure out what each additional increase of a year of education is going to do to predict their outcome on voting. There you go. That's basically what logistic regression is. Now let me show you how to do it with a real example. The example that I've been talking through on the other screencasts for this SPSS module have dealt with a data set that I am using in some of my own research to predict the likelihood or the probability that someone will think that, generally speaking, men make better political leaders. And what I've done here is I've erased almost all of the other variables in the data set so that we can concentrate just on these four. Male lead 2 is the variable, my measure of people who said that they think that, generally speaking, males make better political leaders than women. And so that is a 1 if you think that, 0 if you don't. It's a dichotomous variable, and so we're going to use logistic regression to be able to predict that. Church 4 is a 4-range variable, and as you can see here, you were coded 0 if you never go to church, 1 if you seldomly do, or a few times a year, 2 means 1 to 2 times monthly, and 3 means at least weekly. And when we do a logistic regression involving this particular variable, what we'll be talking about is, for each increment up this 4-point scale, how does that increase or decrease the likelihood that you are or that you would fall into the category of being someone who thinks that, generally speaking, males make better political leaders than women. We might hypothesize, in fact that's what we'll be testing here, we might hypothesize that people who go to church, the more you go to church, the more likely you are to have traditional values and to think of a traditional society as having more value. And as a consequence, it could be that you might also have assumptions about traditional roles for women. And so we'll be examining whether those people, generally speaking, controlling for the influence of these other variables in the model, are more likely or less likely to think that males, generally speaking, make better leaders than women's. Obviously, we've got a dichotomous variable, 0 and 1. You were 1 if you were male. In this case, our output will simply say, how does being a man increase or decrease your likelihood of agreeing that, generally speaking, males make better leaders? And finally, I've got an interaction term here, male by church 4. And what this assumes is that there may be a separate effect between males and females based on going to church or not. If this was statistically significant, what we'd say is, males who go to church are especially likely to believe that males on average are more likely, or rather that males who go to church more frequently are more likely than males otherwise to think that males, generally speaking, make better political leaders. And if this were to be negative, which in the logistic regression we'll be looking at first, if this is statistically significant and our odds ratio is less than 0, what this would mean is that males who go to church are distinct from either people who generally go to church or other males in that they are less likely than we would predict by each of these variables independently. So it may be that males are more likely to say that men make better leaders, and going to church may be more likely to say that men make better leaders, but it could be that the combination of those two is not completely additive, in which case this would be negative, meaning that that particular combination makes you modestly less likely than the full effect of either of these variables by themselves. Let's make it less abstract and let's get it done by analyzing our sample of 2,000 or so respondents. And so what we're going to do here is we're going to run a logistic regression. I'm going to go to Analyze, to Regression, and to Binary Logistic Regression. Binary means 0 or 1 outcome, or a two-point outcome. And so as you can tell, I've already put these variables in the model. We're not going to do anything fancy here, so we'll just hit OK. I'm going to run the analysis rather than pasting it into my syntax. And what do we find? This tells us how many cases were processed. 2,250 cases were processed. This tells us what the dependent variable was coded as. And most importantly, as we begin to move down, this particular data down here towards the bottom, right here, tells us, because this is statistically significant, it tells us that this particular model does in fact explain to some degree whether or not somebody's likely to say that, generally speaking, men make better political leaders. If we go down here to the pseudo R-squared, we've got two different measures here. Generally speaking, the Nager-Eichel is going to return a modestly higher statistic, and that's because the Cox-Snell R-squared cannot actually equal 1, and so it's been modified in this particular measurement. This is not exactly the same as R-squared, which is used in multiple regression, but a loose interpretation of this would be that two things. First of all, this model, not surprisingly, is not extremely powerful. The vast majority, nearly 98% of the variation that we find in whether or not somebody's going to say that men, generally speaking, make better political leaders, is explained by variables that aren't in the model. So that's one of the things that it tells us. The other thing that it tells us is that well, actually, let's just leave it right at that. I think that's for our purposes right here, probably that. Let's just focus on this one. It's not exceptionally powerful. That said, we know the model tells us something. Human behavior is very, very hard to predict, and you will, in fact, find statistical models which are published all the time in which the estimated R-squared is extremely low, especially when you're dealing with individual behavior. So we know that the model matters. Now let's go on and let's look at the predictions. To do that, we go down here to the bottom. And we've got various bits of information in this table, but the most important are these: the EXP and then the B, which means exponentiated betas, called in almost every article out there odds ratios. And what an odds ratio does is it tells you what the change in the dependent variable is, in this case the likelihood that you will think that, generally speaking, men make better political leaders, how it changes with every 1 unit increase in the independent variable. So recalling that the church variable has 4 different values, 0, 1, 2, or 3, each increment on that scale would increase the odds by about 1.27. Another way to think about that is to say it would go up about 27% for each increment. You put that together, that's about a 100% increase. Now, I'm going to show you in another screencast how we can talk in terms that more of us are readily familiar with, probabilities. But keep in mind that a 200% increase, if the number of people who originally thought that men, generally speaking, make political leaders is 10%, that's only going to move it to 20%. So it's a doubling of what the probability or the likelihood would have been anyway. It doesn't mean that as you went from church to the bottom, you go from 0% to 100%. So basically, we've got a significant variable here. We know because it's statistically significant. And if you went from 0 to 4, you've got 4 times 0.27 here. That tells us that you've got about a 100% or an increase or a doubling of when we compare those who go to church once a week to those who never go to church. Our male variable, not surprisingly, we find that all other things being equal, men are about 1.5 times as likely, and again, we don't know what that base number is, but about 1.5 times as likely as non-males, in other words, women, to say that generally speaking, men make political leaders, or better political leaders. Our male by church for statistic is not significant, and we can tell this because it's not below 0.05, which would be the appropriate threshold in this type of a study with this number of observations. And 0.42 means it's not statistically significant. So how do we interpret that? What we say is that being male has an impact. Going to church has an impact on whether or not you're likely to think that males make better political leaders. They both positively impact that, which is to say they both make it more likely that you'll say that men make better political leaders. But being male and going to church with ever more frequency doesn't dramatically increase or decrease what we already know from the other two variables. You're welcome to do what you want, but unless I had some important theoretical interest in a variable, I would actually probably rerun the model normally without this variable, without the interactive term in the model, so that I could because I already know that it's not significant, so that I would get better estimates on these two particular models. In summary, what you want to do when you run a logistic regression model is you want to see how well the overall model looks. That means that you need to look at what's called the chi-square statistic, and you're going to look at that model significant statistics. If it's significant, it means that the model works at least to some degree. The Nager-Eichel R-squared is going to give us a measurement of how well it works. And where this can be most useful frequently is if you add a couple of additional variables to the model and you find that that R-squared is not going up, you may decide, okay, well, those models are not telling us very much. On the other hand, if you add a whole bunch of new variables to the model, that's going to tell us that those additional variables are adding quite a lot if that R-squared goes up significantly. Finally, with respect to the individual variables, what you want to do is recognize what the specific measurement is. Is it 1 increment, 2 increment, 3 increment, etc.? And for each increment in the variable at an increase, then you want to look at the odds ratio. If it's 1, it's not going to be significant because that means that there's no influence. If it's less than 1, let's say it's 0.8, what that means is the odds are reduced significantly as we go in the other direction. So let's say, for example, that we had female here. I can already tell you, based on what we found with male, if we would have had a female measurement, the odds would be significantly under 1. Meaning that that males, or rather females, on average and controlling for other model or other variables in the model, were significantly less likely than men to believe that, generally speaking, men make better politicians. And that is, in a nutshell, what we do with logistic regression. If you're using this in a paper or you're using this in a research project, you're probably going to want to watch the sibling demonstration that's going to come along with this, that will take all of this stuff about talking in odds that's a bit complicated and translate this into probabilities so that we can talk about the base probability that somebody will do something and how each unit increase in church, for example, increases that probability by a certain number. So it might be that you're 25% likely to say that, generally speaking, men make better political leaders, just an average, but it might be that those who go to church at least once a week are, in fact, I don't know, we'll call it 28% likely. And so in many ways, if you're doing something serious with the project, it makes sense to try to translate your data away from odds ratios into probability statements. However, because it takes quite a lot of time to do do that, I almost always run my models first looking at odds ratios to give me a sense about what's going to matter and what's not, because I can tweak my variables before I go into the hassle that's related into converting these various odds ratios and these logistic coefficients into something that's a bit easier to read. And that's it. That's how you do logistic regression.